You ever notice how, like, even the simplest things can be, like, crazy complicated once you start looking closer?
Yeah, definitely.
Like today, we're talking about the physics of a falling ball.
A falling ball.
Yeah. Sounds kind of basic, right? But trust me, it's way more interesting than you might think.
Oh, I bet.
So, how much do you know about, like, the whole gravity thing?
Well, everyone kind of knows it's there, right?
Right.
But it's one of those things that's easy to take for granted,
Yeah. Until you really start thinking about it, you know?
right?
And that's what we're doing today.
Awesome.
And to help us out, we've got some cool source material from a workshop they held in Singapore.
In Singapore.
Yeah, back in 2011. And get this, they were using video analysis to, like, totally dissect the motion of a falling ball.
Wow, so they really broke it down.
Totally. It gets pretty detailed.
Cool.
And they use this software called Tracker to analyze the video, like frame by frame.
Tracker.
Yeah. It's free, too, which is pretty amazing. Anyone can download it and start analyzing videos.
So anyone can become a physics detective.
That's the idea.
I like it.
So with Tracker, they were able to pinpoint the ball's position in each frame of the video. Pretty neat, huh?
Yeah, that's impressive.
And then from that, they could make graphs. Like the ball's vertical position over time, its velocity, even acceleration.
So they're making graphs from a video. That's cool.
Right.
So is it like a dot on a screen moving up and down or something like that?
Pretty much.
Cool.
And the shapes of these graphs are what's really fascinating. So, for example, the graph of the ball's vertical position over time, it forms a parabola.
A parabola.
Which is like that U-shaped curve you might remember from, math class.
I vaguely remember those, yeah.
But when you think about it, that shape tells us a lot about how the ball is moving.
Oh, so it's not just a random shape.
Not at all. So, like, as time passes, the ball's position is changing, but it's not changing at a constant rate, right? It's accelerating downwards. And that's represented visually by that parabolic curve.
Okay, I think I get that. So the parabola means it's speeding up as it falls.
Exactly. So we're already seeing the effects of gravity in the shape of that graph.
That's pretty cool, seeing it visually like that.
And they made other types of graphs too, like plotting the ball's vertical velocity against time.
And what did that look like?
That one forms a straight line.
A straight line.
Now remember, velocity is like the speed and direction of something.
Right, right.
So a straight line on that graph means the ball's velocity was changing at a constant rate, which basically means it's experiencing constant acceleration.
Oh, I see. So it's another way to see that gravity is pulling on it the same amount all the time.
Exactly. We already sort of knew that from the parabola.
Yeah.
But this is like confirmation from a different angle. The parabola showed us the effect of acceleration on the ball's position, while this straight line is showing us the acceleration itself.
I see. So like two sides of the same coin.
Exactly.
That's really neat. Just from this video, we can see how gravity works in multiple ways.
Yeah. It's amazing what you can learn from just analyzing the motion of something so simple.
It makes me wonder what other secrets we're missing out on.
There are tons, I'm sure. Oh, and there's one more thing these graphs can tell us. This is really cool. The workshop materials mention how they calculate the area underneath the velocity time graph.
The area under the graph.
Yeah, sounds kind of like a weird math thing, right?
Yeah.
But it's actually super useful because, get this, the area under that graph actually represents the ball's displacement, meaning how far it traveled during a specific time.
Whoa. So it's not just an abstract math idea?
Nope. It's telling us real information about the ball's movement.
Okay, that is really cool.
Yeah. But wait, there's more.
There's more.
There's always more. The source material also mentions something called Data Builder.
Data builder.
Yeah. It's a tool within Tracker, and it can be used to define the ball's potential energy and total energy.
Energy. We're talking about energy now.
Yep. This is where things get even more interesting.
So it's not just about motion anymore.
Right. Because a ball's motion is connected to its energy. Think about it. When you hold a ball up high, it's got a lot of potential energy just sitting there because of its height.
Okay, so it's like a coiled spring or something.
Exactly. Like it's storing up energy ready to be released.
Got it.
And as it falls, that potential energy starts changing into kinetic energy. Kinetic energy, which is the energy of motion. The ball is picking up speed, right? That speed is a direct result of that kinetic energy.
Okay, so it's like a trade-off. The higher it is, the more potential energy it has. But as it falls, it loses that energy but picks up speed.
Yeah. It's like a constant back and forth.
Fascinating.
And the total amount of energy in the system, it stays the same throughout the whole process.
Oh. So like that law, the conservation of energy.
Yeah. Even though the energy is changing forms, it's never lost. It's like on a roller coaster, you climb up slowly, building potential energy, and then whoosh, all that energy turns into kinetic as you go down the hill.
I love roller coasters.
Me too. Okay, but here's the thing. If energy is conserved, why doesn't the ball bounce back up to the same height every time?
Yeah, shouldn't it keep going forever if the energy is always there?
Right. That's where things get even more interesting. But I think we need to save that for the next part of our deep dive because we are running out of time.
Okay, sounds good.
We'll be right back. All right, so we were talking about how the ball doesn't bounce back up to the same height every time, even though energy is supposed to be conserved.
Right. Yeah, that's a really good point.
Like, what's going on there?
Well, the thing is, in a perfect world with like no air resistance or any friction,
Mm-hmm.
the ball would bounce back to the same height forever.
Oh, so it's like a theoretical thing?
Exactly. It's just that in the real world, there are other forces at play,
Yeah, that makes sense.
I guess.
So what are those forces? Like, what's making the ball lose energy?
So one big one is air resistance.
Air resistance,
Like,
right?
as the ball moves through the air, it bumps into all those tiny air molecules, and all those collisions create friction, which slows the ball down.
So it's like the air is trying to hold it back.
In a way, yeah, and some of that kinetic energy gets converted into heat because of the friction.
So it's like the ball is heating up the air as it falls.
It is.
Yeah.
Just a tiny, tiny bit, though. You wouldn't even notice it.
That's still pretty wild. So is that the only way it loses energy?
Not quite. There's also energy lost when the ball hits the ground.
Oh, yeah. Makes sense.
Like when you hear that thump sound,
Uh-huh.
well, some of that kinetic energy is being converted into those sound waves.
Oh, wow. So it's like the ball is making a sound with its energy.
Yeah, basically. And then there's also some energy lost as heat because of the friction between the ball and the ground.
So it's like air resistance and then impact with the ground are the two main things.
Yeah, those are the big ones.
Wow. So even something as simple as a bouncing ball has all these different things happening with the energy.
It's amazing, right? And this is where that data builder tool we were talking about comes in.
Oh, yeah. You mentioned it before, but I still don't really get what it does.
Okay, so remember how the source material mentioned using data builder to define the ball's potential energy and total energy?
Yeah.
Well, with data builder, you can go beyond just like watching the ball move on the screen.
Yeah.
You can actually quantify the different types of energy at any point in time.
So they could see exactly how much potential energy the ball had at the start and how much of it turned into kinetic energy as it fell.
Exactly.
And they could see how much energy was lost because of air resistance and the impact.
Yep. They can even calculate how much energy was lost as heat and sound.
So they could literally see how much energy went into making that thump sound.
That's the power of data builder. It lets you really break down all those energy transformations.
That's pretty cool.
Yeah, it's really neat. And it shows how energy is never really lost. It's just transformed into different forms.
Like that thump sound is proof that the energy is still there. It's just become sound energy now.
Exactly. And this whole thing makes me think about like the bigger picture, you know?
What do you mean?
Well, the ball eventually stops bouncing.
Yeah.
But all that energy, it doesn't just disappear. It has to go somewhere.
That's true. So where does it go?
Well, it spreads out into the environment.
Like into the air?
Yeah, so the ball heats up the air and the ground a little bit with each bounce.
So the room is getting a tiny bit warmer because of the bouncing ball.
Exactly. That heat energy dissipates into the surroundings and becomes part of the overall thermal energy of the room, the building, even the planet.
Whoa, that's kind of crazy to think about a tiny bouncing ball affecting the whole planet's energy.
It is pretty wild.
Yeah.
But it just goes to show you how energy is interconnected. You know, it's all part of one big system.
So what you're saying is even though the ball stops bouncing, the energy is still out there somewhere.
Absolutely. It's never truly gone. It's just been spread out and transformed into other forms.
It's pretty deep.
Right. And in the next part of our deep dive, we can explore those ideas even further. We can talk about the broader implications of energy conservation and how it all connects to the fundamental laws of physics.
I am ready for that.
Hmm.
Let's take a quick break, and then we'll be back to unlock the secrets of energy. All right, so before the break, we were talking about how that energy from the ball spreads out into the environment.
Right. Exactly.
But I'm still kind of stuck on this data builder thing.
Yeah.
Like, can we actually see the numbers changing, like the exact energy values?
Oh, yeah, definitely. Like, imagine you have these graphs,
Right.
and they're showing you how the ball's potential energy is decreasing as it falls.
Uh-huh.
But at the same time, its kinetic energy is increasing.
Right.
And you can actually pinpoint the exact moment where they're equal, like halfway down.
Oh, wow. So it's like a perfect crossover point?
Yeah. Like you can visually see that energy conversion happening.
That's so cool. And Data Builder can do that?
Yeah. And it can also calculate the exact amount of energy that's lost with each bounce. Like you can see how those values are decreasing over time.
So you can see exactly how much energy is going into the sound and the heat?
Exactly. It's like you're measuring the energy of that thump sound.
That's incredible.
And it really highlights how energy is never truly lost. It's just changing forms.
Right, like that thump sound is proof that the energy is still there. It's just become sound energy.
Exactly. So even though the ball eventually stops bouncing,
Yeah.
that initial energy, it doesn't just disappear.
So where does it go?
It spreads out into the environment like we were talking about.
Right, so the ball is heating up the air and the ground a little bit with each bounce.
Exactly. And that heat energy just kind of dissipates into the surroundings.
So like the room gets a tiny bit warmer.
Yeah. And eventually it becomes part of the overall thermal energy of like the whole planet.
It's crazy to think that dropping a ball could actually affect the Earth's temperature, even if it's just a tiny amount.
I know, it's pretty mind-blowing. But it just goes to show you how everything is connected.
It's like this chain reaction, but with energy instead of dominoes.
Yeah, and that's the amazing thing about energy conservation. It's this fundamental principle that affects everything.
From a tiny bouncing ball to the entire universe. Wow, this has been such an interesting deep dive. We started with a simple falling ball, and now we're talking about the laws of physics.
And it all started with that workshop in Singapore back in 2011.
It's amazing what you can learn from something so simple.
I know, right? It just goes to show you that there's wonder to be found everywhere.
Yeah, like even in a falling ball.
Exactly.
Right.
So next time you see a ball drop, maybe you'll think about it a little differently.
Yeah, I know. I'll be thinking about all those energy transformations and that thump sound.
And the fact that it's all connected to the universe.
That's right. Well, that's all the time we have for today. Thanks for joining us for this deep dive into the physics of a falling ball.
It was fun.
And remember, keep exploring, keep asking questions, and keep looking for the wonder in the world around you.